In the cold vacuum between Mars and the gas giants, a door is currently closing. We are standing on the precipice of a missed connection that will not return for millions of years. As I speak to you now, the interstellar object designated 3I Atlas is hurtling toward its closest approach to Jupiter. It is moving with such ferocious speed that the gravitational grip of the Sun cannot hold it. It is not falling into an orbit. It is escaping, and we are watching it go. This is the reality of the situation right now. The tracking data from the Minor Planet Center confirms that the object, initially spotted by the Atlas survey in Chile just last July, is currently inbound for a rendezvous with the King of Planets on March 16th. That is less than a month away. While headlines have been claiming for weeks that the object has already vanished, the mathematics tell a different story. It is still here. It is threading the needle of the outer solar system, preparing for a gravitational interaction that will slingshot it into the dark. But here is the anomaly that no one is talking about loudly enough. The velocity of this object is 58 kilometers per second. That is its hyperbolic excess velocity, the speed at which it will leave our system forever. To put that into perspective, the fastest object humans have ever launched, Voyager 1, is traveling at roughly 17 kilometers per second relative to the Sun. 3I Atlas is moving more than 3 times faster than our best efforts after nearly 50 years of flight. If you are finding value in this analysis of real-time orbital mechanics, make sure you are subscribed so you do not miss the updates as we track this exit trajectory. The speed is the problem. It is the reason why the European Space Agency's Comet Interceptor mission, which many hoped would be our first hug with an interstellar visitor, is currently sitting on the drawing board instead of at the Lagrange point. That mission was designed to wait, to loiter in space, and ambush a target. But you cannot ambush something moving at 58 kilometers per second with conventional chemical rockets. The geometry simply does not work. The energy requirements to catch up to an object moving that fast on a hyperbolic trajectory that barely skimmed the inner solar system are beyond the capacity of standard propulsion. So we are left with a ghost. We saw it pass perihelion in October 2025. We tracked it past Earth's orbit in December, and now we watch it approach Jupiter. The frustration in the astronomical community is palpable because we know what happens next. After March 16th, gravity will do its work, bending the trajectory slightly, but the kinetic energy of this traveler is too high to be captured. It will not stay. It will punch through the gravitational web of the giant planets and fade into the interstellar medium. But why does this specific velocity matter so much? Why is 58 kilometers per second the number that breaks our current capabilities? It comes down to the tyranny of the rocket equation. To catch 3I Atlas, a spacecraft would not only need to match that exit speed, it would need to exceed it to catch up. And it would need to do so quickly enough that the target hasn't already traveled light years away. A standard launch from Earth, even with a Jupiter gravity assist, would leave a probe drifting hopelessly behind, watching the comet shrink into a star-like point of light that never gets any closer. This feels like a defeat. It feels like the universe has thrown a diamond through our window and we are too slow to catch it before it hits the floor. But what if the speed itself is the key? What if the very thing that makes 3I Atlas impossible to catch is also the clue to how we could do it? There is a group of physicists who have been looking at this problem, not with despair, but with calculation. They are looking at the energy charts, and they have noticed something strange in the numbers. They argue that we are thinking about the problem backward. We are trying to chase a bullet by running after it. But there is another way to generate speed in space, a way that is terrifyingly dangerous but mathematically sound. It involves doing something that goes against every survival instinct we have as a species. Instead of chasing the object out into the cold dark, we would have to turn our backs on it. We would have to fall. The proposal comes from the Initiative for Interstellar Studies, and it involves a maneuver so extreme that it has rarely moved beyond theory. It suggests that the only way to catch the fastest object we have ever seen is to dive into the fire of our own star. The calculations exist now. They point to a launch window in the mid-30s. But to understand why this works, we have to stop looking at Jupiter and turn toward the center of the solar system where gravity is deepest and heat is lethal. The question is not simply whether we can build the ship. The question is whether we are willing to send it into a region where metal softens, electronics fail, and precision errors mean death, all for a scientific answer that might not arrive for 50 years. Because the anomaly of 3I Atlas is not just its speed, it is where it came from and where it is going. And if the trajectory analysis from the Initiative for Interstellar Studies is correct, then the chase has not ended. It has not even begun. To catch something moving at 58 kilometers per second, you do not run after it. You let it go. You turn your spacecraft around and aim it directly at the sun. This is the counterintuitive brilliance of the Solar Oberth maneuver, the concept articulated by Adam Hibbard and his colleagues. It sounds reckless until you look at the orbital mechanics. The principle, first described by Hermann Oberth, is deceptively simple. A rocket engine produces more useful orbital energy when fired at high velocity. The faster the spacecraft is already moving, the more kinetic energy you gain from the same burn. Energy scales with the square of velocity, and the highest possible velocity in the solar system occurs at the bottom of the sun's gravity well. Here is the architecture. A probe of roughly 500 kilograms is launched on a super heavy vehicle, something like a refueled starship in low Earth orbit. Instead of chasing 3I Atlas outward, the spacecraft heads to Jupiter. But Jupiter is not used to fling the probe into deep space. It is used to reshape its solar orbit so that it falls inward. Jupiter becomes a pivot point, bleeding away orbital momentum and sending the spacecraft plunging toward the sun. The fall is violent. The craft drops from the orbit of Jupiter, crosses the asteroid belt, passes Mars, Earth, Venus, Mercury, accelerating every second under the sun's pull. By the time it approaches perihelion, it is moving at hundreds of kilometers per second, faster than any object humanity has ever built. The target perihelion is 0.015 astronomical units, about 3.2 solar radii from the center of the sun. It is skimming the surface of a star. At that exact moment, when velocity peaks, solid rocket motors ignite. They deliver 8 to 10 kilometers per second of delta V. In deep space, that burn would be respectable but not extraordinary. At the bottom of the gravity well, amplified by the Oberth effect, it becomes transformative. The burn converts into a massive increase in hyperbolic excess velocity. The spacecraft does not simply accelerate, it is flung outward. The new outbound trajectory, according to the trajectory analysis, is energetic enough to overtake 3I Atlas decades later. No fusion, no antimatter, no speculative propulsion, just gravity, timing, and chemistry. But this is where physics meets engineering reality. At 3.2 solar radii, the thermal environment is beyond anything routinely attempted. The solar intensity is thousands of times greater than at Earth. The heat shield must withstand flux capable of melting steel within moments. The spacecraft must remain entirely within the shadow of its own shield. A fraction of a degree of misalignment exposes instruments directly to the sun and ends the mission instantly. Radiation levels surge. Charged particles bombard electronics. The burn must occur autonomously while the spacecraft is moving at hundreds of kilometers per second through a turbulent environment shaped by solar wind and magnetic storms. If ignition fails, the probe becomes debris. If the thrust vector is slightly misaligned, the spacecraft misses the intercept by millions of kilometers decades later. The tolerances are unforgiving. The proposed architecture relies on solid rocket motors because liquid propellant management at those temperatures becomes a systems nightmare. Solid fuel is dense, stable, and can be buried deep within the thermal shadow. But it must ignite cleanly and burn precisely while the structure is under extreme stress. We are talking about threading a needle while riding a roller coaster through a blast furnace, and yet the mass budget, 500 kilograms, allows for more than survival. It allows for high-gain communications, nuclear power sources for the long cruise, and a suite of instruments capable of high-resolution spectroscopy during the flyby. Solar panels are useless in the outer darkness. The probe must carry radioisotope power and survive decades of cosmic radiation. After the burn, the violence ends. The spacecraft climbs back out of the sun's gravity well. The roar fades. The thermal storm subsides. It crosses Mars again, then Jupiter, then Saturn, moving faster than any human-made object has ever traveled. And then comes the silence. The probe enters the long cruise phase, decades of pursuit through the outer solar system. The intercept, if the calculations hold, would not occur until the late 2070s or early 2080s. The scientists designing the heat shield today may not be alive to see the images return. It becomes a cathedral project, begun by one generation and completed by another. And yet, even as we debate the engineering, there is a shadow in the data. 3I Atlas has not behaved exactly like a textbook comet. It has not displayed dramatic outbursts, yet it is not entirely inert. There are slight deviations in its motion, subtle, whisper-thin discrepancies that demand explanation. In cometary physics, non-gravitational acceleration is common. Sublimating ice acts like a weak thruster. But the pattern matters. The light curve behavior matters. The rotation state matters. Some researchers urge caution. Comets are chaotic. Dust and ice create complex signals. But uncertainty is precisely the point. The mission is not just about catching a rock. It is about closing the loop on that uncertainty. If there is even a fraction of a percent chance that 3I Atlas represents something unusual, an extreme ejection event, an exotic composition, or something we have not yet categorized, then a flyby becomes scientifically transformative. But to earn that answer, we must pass through fire first, and once the burn is complete and the sun shrinks behind the spacecraft, the drama ends and patience begins. The roar of the maneuver fades into vacuum. The probe cools. It coasts outward into the dark, chasing a coordinate in space for decades. What follows is the long silence. The probe will cross the orbit of Mars, then Jupiter, then Saturn. It will pass the orbit of Neptune and head into the Kuiper belt. It will be traveling faster than any object humans have ever built, gaining ground on 3I Atlas with every passing year. But the distance is vast. If you enjoy exploring these deep technical challenges, take a second to like this video. It helps the algorithm find other people who care about orbital mechanics. The timeline is the final hurdle. A launch in 2035 means the intercept happens around 2085. That is 50 years. 50 years of keeping the deep space network listening for a faint signal. 50 years of keeping the software updated, the team funded, the knowledge fresh. In an era of quarterly reports and 4-year election cycles, who signs the check for a 50-year mission? Who dedicates their career to a spacecraft that will only reach its destination after they have retired? This brings us to the human component of the equation. This is not just a physics problem, it is a sociological one. We are looking at a multi-generational relay race. The team that designs the heat shield will not be the team that analyzes the photos. The pilot who launches the rocket will be an old man or woman when the data arrives. We have to ask ourselves, are we still a civilization capable of that kind of patience? Or has our attention span shortened to the point where an interstellar chase is culturally impossible, even if it is technically feasible? Because while we debate the budget, 3I Atlas is not waiting. It is moving, and the window to catch it is governed by the positions of Jupiter and Earth. It is a clockwork mechanism that does not care about our fiscal years. But there is one more twist in the data. One more reason why this specific object might be worth the half-century wait. As we model the trajectory forward, projecting the path of 3I Atlas into the deep future, we realize that its destination isn't random. It is heading toward a specific region of the galactic plane, a sector of the sky that is dense with stars. Is it a messenger, or is it just debris? To answer that, we have to look at the philosophy of the wager itself. What are we betting, and what do we stand to win? The void is patient. It does not care about human urgency. If we launch the interceptor in 2035, the spacecraft will spend decades as a silent speck of metal drifting against the stars. This is the long silence, the phase of the mission that tests our species' commitment more than our engineering. For nearly 35 to 50 years, the probe will simply coast. It will be too far from the sun for solar power, relying on the slow decay of its nuclear batteries to keep the computer awake and the heaters running. It will wake up occasionally to chirp its status back to Earth, a signal taking hours to cross the abyss, confirming that it is still alive, still on course, still hunting. During those decades, Earth will change. governments will rise and fall. Technology will evolve in ways we cannot predict. The scientists who conceived the mission, Adam Hibbard, T. Marshall Eubanks, Andreas Hine, will grow old. The graduate students who write the code for the encounter sequence will become the senior directors of the project. This is a deferred ambition. It is a concept that is rare in modern spaceflight, which typically demands results within a decade. But the Initiative for Interstellar Studies is proposing a return to the cathedral, thinking of the past, where the foundation is laid by people who know they will never see the spire. The target, 3I Atlas, will simply be a coordinate in the database. A ghost moving ahead of us. We will not see it. We will not receive new data from it. We will only know it is there by the math that governs its flight. But why chase this specific ghost? Why commit a generation of resources to 3I Atlas? Because of what it represents. Interstellar objects are the only samples of other star systems that we can touch. We cannot travel to Proxima Centauri or Wolf 1061. The energy requirements for manned or even robotic interstellar travel are centuries away from being trivial. But the galaxy is throwing pieces of itself at us. 3I Atlas is a sample return mission where the sample has come to us. It is a piece of another world, a fragment of a crust, a shard of a planetarismal, or perhaps something stranger that has crossed the light years to pass through our neighborhood. To let it leave without taking a close look is to turn down a gift from the universe. The whispers of its anomalies might be nothing. The light curve irregularities might be simple tumbling geometry. The lack of outgassing might just mean it is an old, dead rock. But what if it isn't? Scientific history is littered with discoveries made because someone bothered to look at the boring noise in the data. The discovery of pulsars, the cosmic microwave background, the structure of DNA, all appeared as anomalies first. 3I Atlas presents us with a contradiction. It is a comet that doesn't act quite like a comet, on an orbit that implies it was ejected with violence from its home system. And during the long silence, while the probe is cruising, our telescopes on Earth and in orbit will continue to study other interstellar objects. We are building the Vera Rubin Observatory. We are launching the Nancy Grace Roman Space Telescope. We will likely find dozens, perhaps hundreds more of these wanderers. You might ask, if we are going to find more, why chase this one? Why not wait for a slower one, an easier target? The answer is time. The Comet Interceptor mission, the one currently in development by the European Space Agency, is designed to wait for a pristine comet or an interstellar object. But it relies on chance. It requires the object to pass close enough to Earth's orbit to be intercepted with low delta V. 3I Atlas has already passed. We missed the close encounter. But we know exactly where it is going. A bird in the hand is worth two in the bush, but a bird designated by a precise trajectory vector is worth an infinite number of hypothetical future targets. We have the solution for this one. We have the launch window, 2035. We have the method, the Solar Oberth maneuver. Wait for the next one? The next one might be 50 years away, or it might come next year, but be moving at 80 kilometers per second. Or it might come from the solar south pole, where we cannot reach it at all. 3I Atlas is the devil we know. And as the probe closes the distance in the 2070s, waking up from its long slumber, the tension will return. The encounter itself will be brief. At these relative velocities, the flyby will last minutes, perhaps seconds. The spacecraft will have to autonomously track the target, swivel its cameras, lock its spectrometers, and capture gigabytes of data in a blink. The relative speed will be intense. If the calculations from 50 years prior were off by a fraction of a percent, the camera might be pointing at empty space. There is no joystick control from Earth. The light lag will be hours long. The robot is on its own. It has one chance, one shot to justify the decades of waiting and the billions of dollars. If it works, the data that streams back will be the most significant astronomical treasure since the moon rocks. We will see the surface of a visitor. We will know its chemical composition. We will see craters formed by collisions in another star system. We will see the weathering of interstellar dust. But there is a final layer to this story, a layer that goes beyond the science and touches on the existential. If we launch this mission, we are sending a message, not to aliens, but to ourselves. We are telling our future selves that we believed in the value of knowledge enough to plant a tree we would never sit under. And as we approach the final chapter of this investigation, we have to consider the ultimate payoff. When those images finally download, sometime in the late 2080s, what will they show? Will we see a jagged lump of ice, a metallic shard? Or will we see something that forces us to rewrite the history of life in the galaxy? The wager is on the table. The launch window is approaching. The question is, do we have the nerve to take the bet? This returns us to the fundamental question of the wager. The mission to intercept 3I Atlas is not a guarantee. It is a probability game played with rockets and gravity. We are betting technology we haven't fully mastered against a target we barely understand, across a time span that usually crumbles human resolve. But consider the alternative. The alternative is to stand on the shore of our little gravitational island and watch the ships sail past, one by one, without ever trying to board them. The alternative is to accept that 58 kilometers per second is a speed limit on our curiosity. It is to accept that we are stuck here, passive observers of a universe that is teeming with motion. The proposal by the Initiative for Interstellar Studies is a rejection of that passivity. It is an assertion that physics is not a cage, but a ladder. If we can endure the heat of 3.2 solar radii, if we can endure the silence of a 50-year cruise, we can catch the uncatchable. Let's fast forward to the end game. The year is 2085. The interceptor, battered by decades of cosmic rays, wakes up. Its sensors lock onto a faint point of light against the background stars. The relative velocity is closing. The software, written by coders who are now grandparents, executes the terminal guidance sequence. The first photons from the close encounter hit the sensor. The data is buffered, encoded, and beamed back toward the distant spark of the sun. On Earth, a new generation of scientists waits. They are looking at screens in a control room that probably looks nothing like the ones we have today. But the anticipation is the same. The signal arrives. The image builds, line by line. Scenario A. It is a rock, a jagged, strange, dark asteroid from another star. We see tholins, organic compounds turned red by radiation. We see craters. We confirm that the building blocks of planets are the same out there as they are here. This is a scientific triumph. It validates our models of planetary formation. It tells us we are not special in our composition, only in our location. Scenario B, it is something else. The surface is too smooth. The composition is isotopic alloys that don't occur naturally. The shape is geometric. The whispers of non-gravitational acceleration were not outgassing, but something engineered. Even in Scenario A, the boring outcome, we win. We prove that we can navigate the solar system at will. We prove that we can manipulate energy on a scale that turns the sun into a propulsive engine. We confirm that humanity is an interstellar-capable species, at least in terms of reach. But in Scenario B, if that image shows anything artificial, even a dead, derelict shard of technology, then everything changes. The history of the human species divides into before intercept and after intercept. Our place in the universe is instantly redefined. The silence of the cosmos is broken not by a radio signal, but by a physical artifact, and we would have missed it if we hadn't taken the shot. If we had looked at the 58 kilometers per second speed and said, "It's too fast," if we had looked at the solar dive and said, "It's too hot." This is the essence of the deep dive. We analyze the impossible to find the improbable path to the necessary. 3I Atlas is leaving. It will cross the orbit of Jupiter in March 2026, and then it will climb out of the gravity well, slowing down as it goes, but never stopping. It is heading for the stars. The Comet Interceptor mission, the one we have on the books, is a fantastic piece of science, but it is a waiting game. The Solar Oberth mission is a hunting game. It captures the spirit of our species, the part of us that looks at a receding horizon and decides to run. We have the technology. We have the math. We have the target. The only variable remaining is the will. As this object fades from our telescopes in the coming months, remember that its story isn't necessarily over. It might just be the prologue to the longest chase in human history. If you believe we should make the wager, if you believe we should borrow fire from the star to catch the messenger, leave a like on this video. It tells the algorithm that we want more content about the edge of what is possible. And share this with someone who needs to know that the door isn't closed yet. It's just moving very, very fast. We are watching a ghost slip through the keyhole. But we still have the key. We just need the courage to turn it. Until the next deep dive, keep looking up.